that I suspect I might overrun if I don't kick off, I will get going. And if anyone can't hear me, just come up on stage and hit me. So I am talking about fingerprinting of tabletop games. And I think it's worthwhile starting with, there we go, starting with the original research question we were looking at, which was how games, or do games, change fundamentally as we move from 2 to more than 2 players. So multiplayer in this sense meaning at least 3. That's where we started, as you'll see, but as where we ended up isn't quite there, although we partially addressed that. What we ended up also doing was seeing, for multiplayer games, can we use the way that AI algorithms play those games to characterize them and try and describe the games in a way that might be useful or interesting, and potentially even come up with a map of a tabletop game landscape, which is sort of where we end up, but we'll get there in the end. Let's kick off with this motivational research question about games changing as we move beyond 2 players. There are exceptionally good theoretical reasons why games with 3 players or more should be fundamentally different. If you have a 2-player zero-sum game, whether that's tic-tac-toe or chess or Go, then game theory tells us very simply it's an absolute doddle. All you do is you find the Nash equilibrium and you play that, and anything else is just suboptimal. Leaving aside how you find the Nash equilibrium, that whole question or answer falls away once you move beyond 2 players. As soon as you add a 3rd player, the minimax theorem that says that's what you can do ceases to apply. You have all sorts of additional interesting strategic actions coming up. You have coalitions where 2 players can get up against a 3rd, or 3 against the other 2. And you get situations like kingmaking, where you might have 2 players who are vying to win the game, but which of them wins is actually not up to them, it's up to a 3rd player who's going to come last regardless of what they do. So you end up with a very different, a much richer and more chaotic actually set of strategic spaces. That's in theoretical terms, but what about real games that real people play? And in this case, playing games, you can sometimes feel that there is actually a difference, that not all multiplayer games are the same. You have some games which feel very adversarial, such as Risk on the right-hand side, where every move that you make is going to affect the position of another player. You can't avoid doing that, and that applies to their moves as well. And you have other games which are, Snakes and Ladders here is the extreme example, that even if you have 6 players playing the game, any move that you make simply cannot affect the position of the other players. It's just a race to who gets to the winning condition first. It is purely, in this case, multiplayer solitaire. And there are a number of modern Euro-style games which can sometimes feel a little bit like that it doesn't really matter, but I'm playing with other players. And let's make this a bit more concrete. We have here, we're using the tabletop games framework. So we have, we're using 8 games. Now, first of all, I should say thank you to Raluca for going through the tabletop games framework in her keynote earlier today. And I think these are all real games. These are all real games that a lot of real people play. They are not some idea dreamed up by an academic to test an algorithm. These are actual games. A lot of them are very popular. A number of them have won awards. And secondly, they also cover a very wide array of different types of game. So you have the economic engine building of Dominion, you have the push your luck bluff of Diamant, you have perfect information strategy in Dots and Boxes, you have a social deduction game in Love Letter. So these are, hopefully, if we have these in the same framework, we can see how these compare with each other under different algorithms or under other different conditions. And actually, I'll use this opportunity as a selling point that if there's anyone out there who's interested in helping with TAG, whether that's a new iGGi first year or anyone else interested in AI and tabletop games, then please do get in touch. We are very keen to collaborate in any way, shape or form with the tabletop games framework. And we can, the more of us there are, the merrier. So those are the 8 games we're looking at. And the question we're asking is, can we characterize these games, particularly as we change the number of players? Now, A classic AI approach is you pick an algorithm, and let's pick Monte Carlo tree search because, well, frankly, why wouldn't you? And you then pick a number of parameters or variants of that you think might be relevant, and you churn that through some optimization algorithm, and you get this set of optimal parameters that says this is how you play the game well. Or you run several parameters and you compare the scores. But it boils down to finding what's the best way to play this game. We're using this sort of approach, but in a slightly different perspective. So we're not trying to find what is the best way to play this game. What we're asking is, can we characterize games by the algorithmic parameters that seem to be useful addressing this type of game? And we're also not just looking at a single optimal value for each of them. What we're actually looking at is a distribution over those parameters. So we run an optimization 30 times, which gives us 30 completely different sets of optimal parameters. And that gives us a distribution. So that's what we mean when we say a fingerprint. It is a set of 9 marginal distributions over the output of those 30 independent optimization runs. And that gives us much more information than if we just had a single setting. So for example, if you have a very peaked distribution as shown at the top, that all of those 30 runs give you the same answer, then that's telling you potentially something quite important, that that setting seems to be important and interacts with that game in a way that you need to account for. Whereas if you have a very flat distribution that which setting you use doesn't matter, that's telling you something equally useful, which is that something in that game does not engage with whatever that variant of the algorithm is trying to address. And this set of 9 marginal distributions is our fingerprint. And I just emphasize, we're not looking necessarily at the best setting as the thing we're trying to find, although there are some interesting observations on the way. So let's look at an example. This is Uno. So Uno is a high game of deep strategy played by children and families everywhere, and also, according to Charlie's presentation, by a number of sports people. I'm not going to go through the list of parameters on the left. I put that up for any Monte Carlo tree search geeks in the audience who want to go through them. What's important is on the right-hand side, where you can see that set of 9 marginal distributions. And we have the fingerprint for 2-player Uno in green, we have the fingerprint for 3-player in violet, and for 4 players in orange. And let's just pull out this bit in the middle. And you can see when we're looking at these 2 parameters, there is a huge difference as we move from 2-player to 3 or 4-player. That if we just have a single opponent in Uno, then every single one of those optimization runs says you should only use a maximum tree depth of 1, which means you look 1 step forward and then stop. And you should not have a 0 rollout, which means that you never examine any further forward in the game. So that's a very, very short-sighted, very myopic way of playing. And yet this is telling us that's how you play 2-player Uno. But as soon as you move beyond 2-player, that completely ceases to apply, and you have 2 very flat distributions that actually it doesn't really matter how far forward you're looking, or rather it's not as important as it is in 2-player Uno. If we take another example, which is Love Letter. So Love Letter is a very different game to Uno. Uno is, you have a deck of hand cards and you're trying to get them out of your hand as fast as possible, and the person who gets rid of them first wins. Love Letter, you have a roll, a hidden roll, and you are trying to guess what the other players' rolls are and then take appropriate actions to knock them out of the game before they knock you out of the game. And there are 2 first interesting thing here, just to clarify, this is showing us a big difference. If we actually you can see, if we look at Uno and Love Letter, those are 2 very different sets of distributions. And in particular, in Love Letter, we have a very clear thing, regardless of the number of players, that you should always use open loop Monte Carlo search, and you should always redeterminize at the root. Now, to translate what that means you should use information set Monte Carlo tree search when you're playing Love Letter. And that means that it is vitally important what the different possible values are of hidden cards. Now, that might sound quite intuitive. It is a social deduction game. But what is interesting as well is that in Uno, you have just as much, if not more, hidden information in terms of the cards you can't see. But what this is saying is that it's not just the amount of hidden information, love letter, that actually matters. And that comes through very clearly in the way that the algorithms play the game in order to do well. Another thing, and this is perhaps the closest we get to one of our initial research aims, is you can see if we look at the top one in terms of how we move from 2 to 3 and 4 players. Let me run through the opponent tree policy. These 3 settings. Paranoid means what it says on the tin. You assume your opponents are out to get you. You assume they will take the worst possible move they can from your perspective. Whereas Max N takes a slightly more relaxed view and assumes that they'll take the best move from their perspective. And then SelfOnly is a very different approach. What it says is, I'm actually not going to waste any computational budget thinking about what my players, the other players, are going to do. I am purely going to focus my budget on planning my move further into the future. And I will assume they act randomly, and I will just cut them out of that computational expense. And what's in 2-player love letter, you really do need to pay attention and think about what your opponents are doing. But once you move to 3 or 4 player, and especially 4 player, actually sparse computational budget should really be focused on just planning your move. And we have a potentially phase change as we move beyond 2 players. That's part 1. Part 2, effectively what we have here is a sort of very interesting rummaging around in the undergrowth, looking for interesting features in games, looking for comparisons across games. But the next part is to ask, can we take to the air, fly above the forest and look down and get a bird's eye view? And can we collapse each of those fingerprints into a single point and try and come up with a map of games? And we take a very vanilla approach of dimensional reduction with principal components analysis. And what we do is we take each of those distributions, we convert that to a vector of 16 independent numbers, so we have a 16-dimensional space. And then we use PCA and collapse that down to a 2-dimensional space, which tries to preserve as much of the variation and much of the information as we can. This is helpful because obviously a 16-dimensional space is quite difficult to put on a PowerPoint slide, whereas a 2-dimensional space is quite a bit more straightforward. For those who are interested, we did try T-SNE as well as perhaps a sexier algorithm, but it didn't really give anything that's interesting. I think it's possibly because PCA, although it's very simple, it actually works when there is large-scale or potentially linear structure. And in this case, there seems to be, and therefore that's quite helpful in clarifying that. So let's have a look at that map. Now, this is a rather noisy slide. So let me explain briefly what this is. We have 9 points on this plot for each game. That's because we have 2-player, 3-player, and 4-player. And then additionally, for each of those, we use 3 different opponents. We use a random opponent, a one-step planning look-ahead agent, and we use a Monte Carlo tree search agent with a fixed set of parameters. And that's because we want to see if this generalizes. There's no point coming up with a conclusion that only applies if you're playing a random opponent. And what we actually find is that often you want to have the same sorts of settings if you're a random opponent as if you had a much more intelligent Monte Carlo tree search opponent. And you can see that we get some potentially interesting structure. So Uno 2-player, you can see that all 3 of those 2-player Uno points are at the bottom of that diagram, along with dots and boxes. And they are quite different. They are quite clearly separated from the rest of the Uno points. We can also interpret these 2 dimensions, although take this with a hefty pinch of salt. I'm not going to go through the background on the right, unless it crops up in questions. But we can interpret these 2 dimensions a little bit. So what we can say is, as we move across on the x-axis, the games on the right are ones where hidden information matters. We need to use information set Monte Carlo tree search, and then that seems potentially to be linked with only focusing on your move and not worrying so much about what the opponents are going to be doing in any paranoid form. And then as we go from bottom to top, we have games where you really do need to look deeper into the future and search quite a bit deeper down the tree or further forward in time. The Uno and dots and boxes at the bottom, they both have a feature that you get when you take a move, you get an immediate score from that move. So there's very little postponed reward, or that it's clearly not as important as it is in something like Diamant, where you're trying to bluff your opponents over time. So that is a map. As I said, there's several pinches of salt to be taken with this. But one thing I think it's just to finish on is this is a different map where we took 16 dimensions, but rather than taking those from Monte Carlo tree search optimization, we took them from classic game theory, classic game tree setup. So the mean action space, the depth of the tree, the size of the state space. And that's actually something maybe it's less interesting. Everything, apart from dots and boxes over on the extreme left, everything clusters together. And a lot of that is what is actually interpretable is they all have broadly the same amount of hidden information, except for dots and boxes because that has none. But this is telling us that it's not the amount of hidden information that matters, yet there's a quality to that hidden information. And that's what this map pulls out, which perhaps a more standard theoretic map doesn't. So that is a quick run through. Conclusions, we've got a full set of graphs that go through all of the fingerprints for all the games, for any which way you want to cut them at that link. As we found out, of the 8 games, 5 of them did show some indication of a significant change as we moved beyond 2 players, while 3 of them were, it didn't matter the number of players, they seemed to be a little bit more multiplayer solitaire, potentially. We think it's a largely exploratory technique. Well, the question really is, can we use this in game design if we're aiming for a particular point on that map? And is it going to be usable, say, to recommend games which are similar from a play style rather than any keyword match? So with that, I will finish and ask if you have any questions.